Now let's discuss breaking down radicals and simplifying. There's a variety of ways to do this, and I'm going to show you a couple of techniques. Let's start by looking at what we call perfect squares. So I've written 1, 4, 9, 16, etc. How did I get those numbers? 1 is 1 times 1. 4 is 2 times 2. 9 is 3 times 3, etc. So when we look at the square root of a number, so the square root, we use the radical sign. So when we're asked to find the square root of a number, what's being asked is, what is multiplied times itself that would give you the answer A? So if I had something like the square root of 4, the square root of 4 is 2, because 2 times 2 gives me 4. And that's what I've written with the 1, 4, 9, 16, etc. Those are all what we call perfect squares. So when I look at the square root of 100 as my first example, what multiplied times itself gives you 100? And the answer is 10. So now when we look at our next example, it's the square root of 12. Well, there's no whole number or integer multiplied times itself that gives you a 12. Some of you may be thinking 6. 6 times 6 gives you 36 and not 12. So what we have to do is break this down. So here's the first technique. Whenever you're dealing with square roots, what you want to do is use one of the perfect squares as a factor. So what we're looking for is the highest perfect square factor that divides into 12. So what I do is I would start at 9, and 9 doesn't go into 12, so I work my way down. So I choose the one closest to what's called my radicand. The radicand is the number underneath the radical sign. So I look at the highest value closest to 12 without going over, and that would be 9. 9 doesn't go into 12, so I can't use 9, but 4 does. So in simplifying, I rewrite 12 as the highest perfect square factor times whatever value is necessary to give me the 12. So we know 4 times 3 is 12. I use 4 because 4 is a perfect square. I wouldn't have used 6 and 2 because neither 6 nor 2 is a perfect square. So now I simplify. The square root of 4, what multiplied times itself gives you 4, and that would be 2. And so since 3 isn't a perfect square, it remains underneath the radical sign. So the answer to the square root of 12 is 2 times the square root of 3. Now let's look at another example. The square root of 75. So what I do, since 75 isn't a perfect square, I come to the closest perfect square factor of 75, and that would be 64. 64 doesn't divide into 75 evenly, so I'm going to work my way to the left to find one that will. If none do, then it's simplified as the square root of 75. So 64 doesn't go into 75, nor does 49, nor does 36, but 25 does. So I'm going to rewrite 75 as the square root of 25, because 25 is a perfect square factor, and 25 times 3 gives me 75. Notice they're both underneath the radical sign. 25 is a perfect square, so you ask yourself, what multiplied times itself gives you 25, and that would be 5. So our answer would be 5 square roots of 3. Our next example is 3 square roots of 32. So what I'm going to do is look at my perfect square factors. I'm going to find the highest perfect square factor that goes into 32. So I start with 25 because that's closest and work my way down. So 25 doesn't go into 32, but 16 does. If you don't use this approach, this can get you in trouble because there's actually 2 perfect squares that divide evenly into 32, 16 and 4. So if you chose 4, then you wouldn't have broken down the radical into its simplest form. So 16 goes into 32. So what do we do with this 3? So we just keep the 3 in front. So it's 3 times the square root of 16. And 16 times some number gives me 32. And of course, that's 2. So my next step is to simplify the perfect square. So I still have the 3 on the outside. So it's 3 times the square root of 16 is 4, because 4 times 4 gives me 16, and I still have my square root of 2. 3 times 4 is 12, so my final answer would be 12 square roots of 2. Okay, now I want to introduce something different. Now this helps whenever we're dealing with variables. So whenever we're looking at radical signs, so when we're looking at square root, we're going to also be dealing with what we call cube root, maybe fourth root, fifth root, etc. So this number that's up top of the radical is called the index. So the index tells you how many times a number needs to be multiplied times itself to give you the radicand. Okay, so when I look at the cube root of 8, for instance, I'm not saying what multiplied times itself gives me 8. What number multiplied times itself 3 times gives me 8, and that would be 2. And we'll talk about simplifying in a moment. So all of these have indexes shown: cube root, fourth root, fifth root, but square root doesn't. It has an understood index of 2, but it's never shown. Similar to whenever we look at a variable when it's an x, there's a 1 understood in front, but it's never shown. Same thing with square root. So square root means what number multiplied times itself, and again, our index would be 2. So what I'm going to introduce is another process of simplifying, and I use what's called a division of exponents. So what I'm going to do is I'm going to show you this particular problem. I'm going to rewrite it, but I'm going to write the index 2. So that's a to the 7th, b to the 12th, and c to the 15th. So what I do to simplify is I divide the exponent by the index. So for the a, I'm dividing 7 by 2. So 2 goes into 7 3 times with a remainder of 1. Okay, so the number of times that it goes into a specific value is the exponent on the outside of the radical sign. So this becomes a to the 3rd. The 3 again is the number of times that, in this case, 2 went into 7. Now you say, well, what do you do with the remainder? The remainder is the exponent of that factor underneath the radical sign. So when you have a remainder, it remains underneath the radical sign. So let's look at b to the 12th. So I have 12 divided by 2 is 6. So that means 6 are on the outside, and 2 goes into 12 with a remainder of 0. So 0 b's remain underneath the radical sign. Let's look at the next one, c. So we have 15 divided by 2. So 2 goes into 15 7 times with a remainder of 1. So that means we have 7 factors of c on the outside. Since we have a remainder, 1c remains underneath the radical sign. So when we're showing our answer, we don't show the exponent of 1. So our answer would be a to the 3rd, b to the 6th, c to the 7th, times the square root of ac. We're going to be using this approach more, so you'll see more examples coming up. Okay, so the next example is the square root of -9. So the square root of -9, so remember, it's asking us what number multiplied times itself equals -9. Well, there's no real number, because if I multiply a positive times a positive, my answer is positive. You say, well, what about negative? Well, if I multiply a negative times a negative, I also get a positive. Because remember, we're saying what number multiplied times itself equals this number. So if you multiply a number times itself, a positive times a positive or a negative times a negative, you'll never get a negative. So there's no solution under the set of real numbers. Okay, so now let's go through this technique we just talked about a minute ago with the division of exponents. So here we have the cube root. So the index here is 3 of x to the 8th, y to the 12th, z to the 16th. So I'm going to rewrite that. So again, it's the cube root of x to the 8th, y to the 12th, z to the 16th. So we're going to go ahead and simplify. So we're going to start, and you can do this in your head if you want. I just want to show you. So we start with the exponent 8, and on the outside is our index. In this case, the index is 3. So 3 goes into 8 2 times with a remainder of 2. So that means I can take out 2 factors of x, but I had a remainder, so that means 2 still remain underneath the radical sign. Important that you put the index back in as part of your answer. So the next one, I'm going to look at my y. So I'm going to have 12, which is my exponent of y, divided by my index. So 3 goes into 12 4 times with a remainder of 0. So that means I can take out 4 factors of y and 0 remain underneath. So the last is the z. So it's z to the 16th. So I put my exponent, which is 16, with my index, which is 3 in this case. So 3 goes into 16 5 times. So 5 times 3 is 15. That means we have a remainder of 1. So that means I can take out 5 factors, and I have 1 that remains underneath. And again, I don't show this exponent as a part of my answer, but it's understood. Okay, so next, we have the fourth root of 32, a to the 10th, b to the 15th. So we don't divide 4 into 32. Remember, we're just dividing exponents. So what do I need to do to express 32 so it has exponents? I'm going to use the factoring tree. So I'm going to start out with whatever my coefficient is. In this case, it's 32. Since 32 is an even number, I know that 2 will go into it. And I keep breaking down the number. So 32 is 2 to the 5th power. So when I'm rewriting my expression, this becomes the fourth root of 2 to the 5th, because that's what 32 is, a to the 10th, b to the 15th. So now I do my division of exponents. So 2 is raised to the 5th power, so I divide that by my index. And again, my index in this case is 4. So 4 goes into 5 1 time with a remainder of 1. So that means I can take out 1 factor of 2 and 1 remains because of my remainder. Notice again, I put my index 4 back in as a part of my answer. Now I'm going to break down a to the 10th. So I put my exponent 10 divided by my index. Since we're dealing with fourth root, it's 4. So 4 goes into 10 2 times with a remainder of 2. So that means I can take out 2 factors of a, and my remainder was 2, so 2 remain underneath the radical sign. Last, I do my b, that's b to the 15th divided by 4. So 4 goes into 15 3 times with a remainder of 3. So it would be b to the 3rd with b to the 3rd underneath. So my final answer is 2a squared, b cubed, or b to the 3rd power, times the fourth root of 2a squared, b to the third. Another example. Here I have the cube root of 108 x to the 9th y to the 22nd. So remember, we're not dividing 3 into 108. We need to break 108 down into prime factorization. So we're going to start with 108. Since it's an even number, we know 2 will go into it. We know 2 will go into 54. Now, since 27 isn't even, we're going to go to 3. So 108 is 2 to the second and 3 to the third. So we're going to write that as 2 separate factors, 2 to the second, 3 to the third, x to the 9th, y to the 22nd. So now we're going to break it down. So we're going to start with 2. So we have 2 squared. So our exponent is here, divided by 3. So 3 goes into 2 0 times with a remainder of 2. So that means we can't take out any 2's. So the 2 has to stay underneath. So again, I write in my index, and this is 2 squared. Next, I'm going to go to 3 to the third power. So my exponent is 3. My index is 3, and 3 goes into 3 one time with a remainder of 0. So I can take out 1 factor of 3. Next is x to the 9th. So I'm going to take my exponent 9, divide it by my index, which is 3, and 3 goes into 9 3 times with a remainder of 0. So that means I can take out 3 factors of x with a remainder of 0, so no x's remain underneath the radical sign. And now my y's. The exponent is 22. My index is 3. 3 goes into 22 7 times with a remainder of 1. So I can take out 7 factors of y with 1 remaining underneath. So now on the outside, I have 3, x to the third, y to the 7th. Remember, you're going to write in your index, so it's the cube root. We know 2 to the second power. 2 times 2 is 4 times the y. The next, we're going to take square root this time. So again, when I'm simplifying, that -3 stays on the outside. Remember, square root has an index of 2, so I'm going to write it there. 72 we need to break down into prime factorization. Again, since it's an even number, I start with 2. So 72 is 2 to the third times 3 squared. So it's 2 to the third times 3 squared. I still have my a to the 5th and b to the 13th. So now I'm going to divide my exponents. So this -3 still is on the outside. And I have my square root just in case I have remainders, but I'm not going to write the index because it's understood. With square root, you never write the index as a part of your final answer. Okay, so now I do my division of exponents. So I'm going to do it without writing it this time. So I divide 2 into 3. 2 goes into 3 one time with a remainder of 1. So now I go to my 3 squared. So 2 goes into 2 one time, but it went in evenly, so there's no 3's that remain. Next, my exponent of 5. 2 goes into 5 2 times with a remainder of 1. And then for my 13, 2 goes into 13 6 times with a remainder of 1. So on the outside, I'm just going to multiply what I have. -3 times 2 to the first. So -3 times 2 is -6 times 3 to the first. So -6 times 3 is -18. A to the second, b to the 6th times the square root of 2ab. B. So this technique works no matter what your index is. That's why I like it so much. So the first problems that we did where we found the highest perfect square factor, if that's confusing to you, with practice, this is the best way to do it, or maybe the best way. You need to understand both, but whatever you use, make sure you feel comfortable and practice. Our first examples we see two bases raised to exponents that are fractions. We call that rational exponents. So we're going to change so that you understand what it means from rational exponents to radical form. So radical form means, of course, that we're dealing with a radical sign. And our index, the number or our root, is 3. So in this case, this is the cube root. Now, the numerator represents the power in which our base is raised. So there's two different ways to look at that. We can look at this as the cube root of a squared, or we can look at this as the cube root of a with the whole thing being squared. Either is an acceptable form. So now let's look at the next example. We have b raised to the 3/2 power. So again, our index is a 2, and our base is b, and that's being raised to the 3rd power. But remember, in our answer, when we're talking about square root, we don't show the index, it's understood. So our answer to this would either be the square root of b cubed or the square root of b being cubed. So again, rational exponents are just another way to express something that's in radical form, to maybe make it easier to solve, simplify. So now let's get into operations on radicals. So we're going to talk about addition and subtraction, of course, multiplication and division. So our first example, we have 6 square roots of 5 plus the square root of 11 minus 4 square roots of 11. So the first thing that we're going to do is simplify each radical. In this case, these radicals are in the simplest form. In other words, there's no perfect square factors of these. So our next step is to combine like terms. What makes them like is that the radicands are the same. If the radicands are the same, then all we do is add the coefficients. So keep in mind again, when we have the square root of 11, that's really 1 square root of 11. So when we're combining like terms, we only have one term that has the square root of 5. So that's 6 square roots of 5. And then we have 1 square root of 11 minus 4 square roots of 11. So 1 minus 4 is minus 3, and the square root of 11 stays as it is. In our next example, we have the square root of 147 plus the square root of 75 minus 2 square roots of 12. So what you need to do first is simplify each one. So depending on what technique you're going to use is up to you. So we have the square root of 147 that we need to break down. We have the square root of 75 that we need to break down. And we have minus 2 square roots of 12 that we're going to break down. So what I'm going to do is go ahead and use the first technique we talked about whenever we were simplifying, and that's by choosing the highest perfect square factor. So 147 can be broken down into the square root of 49 times the square root of 3. We know the square root of 49 is 7, so this gives us 7 square roots of 3. The square root of 75 can be rewritten as the square root of 25 times the square root of 3. And the square root of 25 we know as 5, so we have 5 square roots of 3. And the square root of 12 can be broken down into the square root of 4 times the square root of 3. We know the square root of 4 is 2. So remember, you're going to take the existing coefficient, which was -2, multiplied times whatever you take out from underneath the radical sign. So here we'd have -2 times 2, which is -4 radical 3. So I'm going to rewrite my original problem into its simplified form. So it's going to be 7 square roots of 3 plus 5 square roots of 3 minus 4 square roots of 3. So remember, I'm combining like terms. Since they all have the same radicand, I'm just going to combine the coefficients. So 7 plus 5 is 12, and 12 minus 4 is 8. So our answer would simply be 8 square roots of 3. Now, if you wanted to have simplified the problems, you could have used that prime factorization, the factoring tree to do this. Or if you're comfortable using the highest perfect square factor, you can do that with square roots as well. So I want you to look at a pattern before we get into multiplication. So when we multiply the square root of 2 times the square root of 2, that equals the square root of 4. Because when you're multiplying radicals, you multiply the radicands together. And if there's a coefficient, you would multiply the coefficients together. But the square root of 2 times the square root of 2 would give you the square root of 4, which is a perfect square. And the square root of 4 is 2. So anytime you multiply a radical times itself, you're of course creating a perfect square. So the square root of 3 times the square root of 3 is the square root of 9, because 3 times 3 is 9. 9's a perfect square, and the square root of 9, of course, is 3. So notice, when you multiply a radical times itself, it's more or less just removing the radical sign because you're creating a perfect square. So the square root of 5 times the square root of 5 equals 5. The square root of 7 times the square root of 7 equals 7. The square root of 17a times the square root of 17a is 17a. The square root of 13 times the square root of 13 is 13. So you see the pattern. So I'd like to show you things to make life easier on you when you're simplifying. So let's go right into multiplication. So here we have 2 square roots of 3 times -4 square roots of 5. So as I said before, we'd multiply coefficient times coefficient. So 2 times -4 is -8. And the square root of 3 times the square root of 5 is the square root of 15. Now the square root of 15 doesn't have any perfect square factors with the exception of 1, the number 1. So therefore our answer is already in its simplified form. So our answer is just -8 square roots of 15. Let's look at our next example. We have 4 square roots of a times the quantity. When I say the quantity, that means what I say next is inside parentheses. 2 square roots of b minus 4. So we use the distributive property. So I multiply 4 square roots of a times both of the terms inside the parentheses. So here I multiply 4 times 2, which gives me 8. And the square root of a times the square root of b is simply the square root of AB. Next, I multiply 4 square roots of a times -4. So 4 times -4 is -16, and I still carry the square root of a with me. Can I combine anything here? The answer is no, because the radicand on the first term is AB. The radicand in the second term is just a. They have to be identical in order to be able to combine the coefficients. The next problem. So here we have the quantity, the square root of 7 minus 4 square roots of 3 squared. This does not mean we square each one individually. When you have the square on the outside of a binomial, what that means to do is you take the binomial, which is square root of 7 minus 4 square roots of 3, and multiply it times itself. So in order to do so, we use the distributive property, or some of you call it the FOIL method. So I'm going to start by taking the square root of 7 and multiplying it times both terms. So the square root of 7 times the square root of 7. Yes, it's the square root of 49, but remember what we just talked about. So what we talked about was anytime you multiply a radical times itself, it's simply removing the radical sign. So make life easier on you. So when I multiply the square root of 7 times the square root of 7, that's 7. Notice it's not underneath the radical sign. Now when I multiply the square root of 7 times negative 4 square roots of 3, I get negative 4, and the square root of 7 times the square root of 3 is the square root of 21. Why is that still underneath the radical sign? Because remember, it only removed the radical sign when I multiplied the radical times itself. Next, I'm going to take negative 4 square roots of 3 times both of the terms on the right. So negative 4 square roots of 3 times the square root of 7 is negative 4. And the square root of 3 times square root of 7, square root of 21. Now for the last, I'm multiplying negative 4 square roots of 3 times negative 4 square roots of 3. Negative 4 times negative 4 is positive 16. And the square root of 3 times the square root of 3 is 3. Remember, radical times itself removes the radical sign. So let's go on further. So what I'm going to do right now is just rewrite the first 3 terms and simplify 16 times 3, which is 48. Now I'm going to combine like terms. So I have 7 plus 48, which is 55, 7 and 48. And then I have like terms because they both have the same radicand. So I add negative 4 and negative 4, that gives me negative 8. And remember, the radicand stays the same. So my answer would be 55 minus 8 square roots of 21. Okay, the next thing I want to do is show you a pattern, again, to make life easier on you later on. We're going to talk about the concept of a conjugate. We're going to use this to rationalize rational radical expressions in a second. But let's look at a pattern. So what is a conjugate? When I look at these factors, x minus 3 and x plus 3, notice they're exactly the same with the exception of one's a subtraction problem, the other's an addition problem. These are conjugates of one another. Look what happens when we multiply a factor times its conjugate. So remember, I'm going to take x times both of x and plus 3, and then negative 3 times both x and positive 3. So I multiply x times x, I get x squared. I multiply x times positive 3, and I get positive 3x. Next, I take the negative 3 times both terms. So negative 3 times x is negative 3x, and negative 3 times positive 3 is negative 9. What happens to our middle term? Notice one's positive 3, the other's negative 3. This is what we got, remember, when we factored the difference of 2 squares. So when we multiply a factor times its conjugate, the middle term is eliminated. That'll have some significance coming up. So let's look at doing it with radicals. So here we have the square root of 5 minus the square root of 3 times the square root of 5 plus the square root of 3. Everything's the same with the exception of one's a subtraction, the other's an addition problem. So these are conjugates of one another. So again, let's use the distributive property. So I start by multiplying the square root of 5 times the square root of 5. Anytime you multiply a radical times itself, it removes the radical sign. Then I'm going to take the square root of 5 times the square root of 3, and that's going to give me positive square root of 15. Next, I'm going to take negative square root of 3 times the square root of 5, and that gives me negative square roots of 15. Lastly, I'm going to take negative square root of 3 times positive square root of 3. So a negative times a positive is a negative, and I'm multiplying the square root of 3 times itself, so it removes the radical sign. Notice my middle terms. They're going to be eliminated. And 5 minus 3 is simply 2. So why am I showing you this? So you can see a pattern and make life easier. For this example, notice there's no radical left in the answer. This is an integer, a whole number, counting number, but there's no radicals left. That's going to play a part in what we do coming up. So what can we do to make life easier? We can find a shortcut. So what's the shortcut for this problem? Well, if we know our middle term is going to be eliminated, notice what we have here. If I multiply the first term times the first term, the square root of 5 times the square root of 5, that removes the radical sign, that's 5. And if I multiply the last two terms together, so a negative times a positive is a negative, square root of 3 times the square root of 3 is 3. The answer is 2. So all I really needed to do in this problem, since I've identified them as being conjugates of one another, is just multiply the first two terms together and the last two terms together. So that being said, let's look at the last example. Square root of 17 minus the square root of 13 times the square root of 17 plus the square root of 13. They're conjugates of one another, right? So what do we need to do to get our final answer? We don't need to go through the distributive property. We know that there's not going to be a middle term, and we know that a radical is not going to be a part of our final answer. So we'll start by multiplying the first two terms together. So the square root of 17 times the square root of 17 is 17. Remember, multiply a square root times itself, it removes the radical sign. Then the last thing I have to do is multiply the last two terms together. So a negative times a positive is a negative, and the square root of 13 times itself is 13. And 17 minus 13 is 4. It's as simple as that. So it's good to learn these patterns, and it's good to understand why it's a pattern as well. So let's look at simplifying rational expressions that have radicals. So the rule will be no radicals are allowed to be in the denominator. So we're going to have to rationalize. So the process of rationalizing means we change an irrational number, a number underneath the square root symbol in this case, to a rational number. That means a number that's not. So how do we do that for the denominator, since we do not want to have an irrational number in the denominator? Okay, what we're going to do is multiply in order to remove the radical sign. So we talked about this twice and in two different forms. So we know by the pattern, anytime that we multiplied a radical times itself, it removes the radical sign. We also learned that when we're dealing with a binomial, when we multiplied an irrational value times its conjugate, we no longer had a radical sign. So we're going to look at what we have and determine what we need to do based on the original problem. So in this case, we have a monomial, so just the square root of 3. So our first step here is going to be to simplify if possible. So we can reduce the fraction if possible. You can only reduce radicals with radicals and rational numbers with rational numbers. So in other words, I can't simplify this any further. So I need to get rid of the radical sign in the denominator. And we know that when we multiply this by itself, it removes the radical sign. So in the numerator, I have 4 times the square root of 3, which is 4 square roots of 3. And in the denominator, when I multiply a radical times itself, a square root times itself, it removes the radical sign. Now, if I could reduce, I would. Remember, I can't reduce something underneath the radical sign with something that isn't underneath a radical. So this cannot reduce any further. So that would be my final answer, 4 square roots of 3 over 3. My next example. Before I get into rationalizing, what I want to do is reduce. So I'm going to rewrite this. Square root of 18a over the square root of 6y. So since they're both underneath the radical sign, I can reduce. So 6 goes into 16 one time and into 18 three times. So right now, in its simplified form, I have the square root of 3a over the square root of y. Okay, so I'm rationalizing the denominator. So since this is a monomial, I know if I multiply the square root times itself, it's going to remove the square root symbol because I'm creating a perfect square. So the square root of y times the square root of y is y. Since both of the factors in the numerator are underneath the radical sign, I multiply those together. So 3a times y is simply the square root of 3ay. And that would be your final answer. Remember, one y is underneath, the other isn't, so I can't reduce this any further. So reduce or simplify first, and then rationalize. Okay, so my next example, notice I have a binomial. Binomial meaning two terms. So I'm going to put these inside parentheses to remind me. They belong together, and I can't do anything separate. So anytime I have a binomial and I'm asked to rationalize, this is where we're going to use the conjugate. So I'm going to multiply numerator and denominator by the conjugate of the denominator. So what's the conjugate in the denominator? So since it's the square root of 11 minus, its conjugate is the square root of 11 plus, and in this case, the square root of 7. Whatever I do to the denominator, I need to do to the numerator as well. The denominator is easy if you use the shortcut. Remember, when I multiply the binomial times its conjugate, no middle term, no radicals left. So all I need to do is multiply the square root of 11 times the square root of 11, which is 11. And negative square root of 7 times positive square root of 7. A negative times a positive is a negative. And the square root of 7 times itself is 7. So I know my denominator is going to be 4. Now the numerator isn't quite as easy to do. Okay, so I'm multiplying the square root of 11 plus the square root of 7 times itself. We did an earlier example when we had a quantity squared that we had to rewrite it and now use the distributive property. So here we have the square root of 11 times both the square root of 11 and plus square root of 7. So we start by multiplying the square root of 11 times both terms. So the square root of 11 times itself, remember, removes the radical sign. The square root of 11 times the square root of 7 is the square root of 77. Next, I'm going to take square root of 7 times both. So this positive square root of 7 times positive square root of 11, again, is positive square root of 77. And then I multiply positive square root of 7 times itself, which, remember, removes the radical sign. So when I worked out the numerator, I got 11 plus the square root of 77 plus the square root of 77 plus 7. Now I'm going to combine like terms. So 11 plus 7 is 18. Now keep in mind, when you're adding radicals, I can add these together because the radicand are the same. They're both the square root of 77. Remember, we don't add those numbers together. We add the coefficient. So here I have 1 square root of 77 and 1 square root of 77, and that gives me 2 square roots of 77. We still have a final step. We're looking for a common factor, if it exists, that will go into all three, 18, positive 2, and positive 4. So since there's a value that divides into all three of these, we divide it out. So since 2 goes into all three of these, we divide a 2 out. So 18 divided by 2 is 9. 2 divided by 2 is 1. So that gives us 1 square root of 77. And 4 divided by 2 is 2. So again, since 2 divides into all 3 of the coefficients, we divide out 2, 1, and 9. So our final answer is 9 plus the square root of 77 over 2. Let's do another one. Here again, we have a binomial in both the numerator and denominator. So I'm going to put that inside parentheses. I need to rationalize. So if I'm rationalizing a binomial, I need to multiply by its conjugate. So the conjugate of the denominator would be the square root of 6 minus, since this is plus, the second one needs to be minus. What I do to the numerator, I do to the denominator as well. So again, let's do the denominator first. The square root of 6 times the square root of 6 is 6. Positive square root of 3 times negative square root of 3 is negative 3. We didn't have to use the distributive property because, again, we know when we multiply a factor times its conjugate, you won't have a middle term. And that's the purpose, so that we're eliminating the radical. So in the numerator, we need to follow through and use the distributive property. So I have negative 6 minus the square root of 3 times itself. So you're going to start by multiplying the square root of negative 6 times both terms in the parentheses to the right. So the square root of 6 times the square root of 6 is 6. Square root of 6 times negative 3 is negative square root of 18. Then we start with negative square root of 3 times both. So negative 3 square roots, negative square root of 3 times the square root of 6 is negative square root of 18 again. And negative square root of 3 times itself, a negative times a negative is a positive, and the square root of 3 times the square root of 3 is 3. Okay, so let's go further with this. Combine like terms, so 6 plus 3 is 9, minus 1 square root of 18 and minus 1 square root of 18 is negative 2 square roots of 18. Okay, now this is where it's just a little bit different. In the previous problem, we didn't have to simplify what was underneath the radical sign. In this case, 18 can be broken down. So we need to simplify as much as we can. So we have 9 minus 2 times the square root of 9 times the square root of 2. So this would give us 9 minus 2 times 3 times the square root of 2. So this would be 9 minus 6 square roots of 2. So again, all I've done is simplified negative 2 square roots of 18 as far as I can. So again, 9 minus 6 square roots of 2. So in the denominator, 6 minus 3 is 3. And the numerator, I have 9 minus 6 square roots of 2. Now I look to simplify further. If something divides into 9, 6, and 3, I divide it out. 3 goes into all 3, so that becomes a 1, a 3, and a 2. I don't show the 1 as a denominator, it's understood. So my answer would be 3 minus 2 square roots of 2 as my final answer. A little bit more complicated, but the process is the same. Okay, the last example. Here I have 2 over the square root of 5x. Square root of 5x is a monomial. I can't reduce 2 and the square root of 5x. So I'm going to multiply by the square root of 5x. So in the numerator, I have 2 square roots of 5x. And remember, when I multiply a square root times itself, it will create a perfect square, which removes the radical sign. You can't reduce because in the numerator, 5x is underneath the radical sign, and in the denominator, it isn't.